pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process pressures and temperatures.
So it can do liquid too, right? Gas and steam, right? Can do everything.
Every differential pressure flow meter manufactured by Andrus and Hauser is configured to customer specifications and
Okay, the rest is just the sales stuff. So Andrus Hauser, couple years ago, when I tried to find the same Coriolis flow meter, Andrus Hauser is cheaper than the what's another one? The Coriolis flow meter from my promotion. That one is somewhat more expensive, okay? But it's also more standard. Yes.
So the pressure change across the diaphragm, not the diaphragm,
the restrict.
What?
that is greater than is the more mass flowing, the lateral flowing, that is
More in this video, it says velocity, volume, and mass, right? But actually, just measure the pressure drop. Just that. Just measure the pressure drop. And we know that the pressure drop is some kind of rho v squared, depending on velocity squared. So when it flows faster, it has more pressure drop. It's not necessarily mass. The diaphragm at the bottom? This thing? The size of the orifice plate. We can have orifice plate, we can have nozzle. In the video it said if we have some solid particle, use nozzle. Or if we want less pressure drop, we can use what? Venturi tube, right? So we need measurable pressure drop, but it should not too much. Got it? So let's say we use orifice plate. Are we going to use the one that have very small hole? Or we want to use the one that have a big hole? How do we decide any of that? There are several kind of holes for the orifice plate, right? It's dependent on flow rate. How much do we flow? If we flow a lot and we use the one that have very small hole. This means it can measure, but it creates too much pressure drop. Okay, you have 50 psi pressure drop across just the flow meter. That's not good, right? So if we have small flow rate and we have big hole for the orifice plate, and I have just 0.1 inch of water pressure drop, is that good? 0.1 inch of water is not measurable. Okay, we cannot measure it accurately. So we need enough pressure drop so that we can measure pressure drop accurately and then convert it back to flow rate. If it is too much, we have to consider to have a bigger hole for the orifice plate, or change from orifice plate to nozzle or venturi tube. Okay, so nozzle and venturi tube is have less pressure drop. There's a precise range on their website. For example, when we actually try to get, hey, what kind of orifice plate we want to use, they want to know how much is the range of the flow rate. And then when we go to the manual, if you download the manual, if you say, hey, for this range, if you want to use this, we recommend model ABCD something. It even tell you model number and like the size. What they need to know is what kind of gas that we want to measure. Okay, just that. Good. So for this video, this picture, venturi, right? And we have Daniel. Venturi, it's not that important, okay? It's not in the test, but just so you know. So orifice plate has most pressure drop. Nozzle have less pressure drop. Okay, that's a nozzle, right? And venturi tube is have least pressure drop. So this is a nozzle, and venturi tube is this one. So what you can see is, if you have gradual change, we have less and less pressure drop. Okay, if we have abrupt change like orifice plate, we have more pressure drop. Okay, and we use that for gas cell line. Do we? Yes. The next one, pitot tube. It's also used differential pressure. Let's say you want to see.
So 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovers a direct relationship between the pressure and speed of a fluid flowing in a pipe. At the same time, the French engineer Henri de Pitot is constructing a device for measuring the traveling speed of ships using flow pressure. His instrument is known as the Pitot tube. Here is how this measurement method works. Pitot tubes have a rod-shaped measuring element that is inserted into the pipeline perpendicular to the flow direction. On the front and rear of this probe are several holes. Two separate tubes connect these holes to a differential pressure sensor. With its two pressure chambers, separated by a diaphragm, the tiniest pressure differences in the flowing fluid can be precisely measured. The individual pressure taps are distributed along the entire pipe cross-section to ensure a representative measurement. If there is strong interference in the flow profiles, it's advisable to fit a second Pitot tube, rotated by 90 degrees. If the fluid is not flowing, the pressure before and after the probe is essentially the same. As soon as the fluid starts to flow, an additional impact pressure against the front of the probe is generated, also known as the dynamic pressure. On the rear of the probe, in contrast, only the static pressure, which is not related to the flow, is still measured. As a result, different values are detected in the pressure chambers of the sensor. Higher pressure against the flow and constant pressure on the rear of the Pitot tube. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and therefore the dynamic pressure, the greater the differential pressure measured. Pitot tubes are able to register the flow in both flow directions, This means that balancing measurements, for example in gas pipeline networks, can be carried out at any time.
So it measures the pressure, upstream and downstream, right? Static and dynamic, and compare that. If they're the same, there's no flow. If there's a lot of different, there's a lot of flow rate. So that is based on the pressure drop. And another one, vortex.
Principle. In 16th century Italy, Leonardo da Vinci observed how vortices form in flowing
Leonardo da Vinci, okay.
Some 400 years later, Hungarian physicist Theodor von Karman described the physical laws that govern how these vortices take shape. Here's how this measurement method works. Inside each vortex flow meter, a bluff body is located in the middle of the pipe. This body is a kind of obstruction that disturbs the flow. Downstream from the bluff body is a mechanical sensor which can register the tiniest pressure differences in the flowing fluid. If the fluid is not flowing, no vortices form. As soon as the fluid starts to move and reaches a certain flow rate, vortices gradually appear downstream of the bluff body. These vortices are detached alternately on either side of the bluff body and are carried away by the flowing fluid. Zones of high or low pressure now appear downstream and thus create a phenomenon that is known as the Karman vortex street. These differences in pressure exactly match the frequency of the passing vortices and are precisely registered by the mechanical sensor, shown here in slow motion. This sensor is unique because it's inherently so well balanced that pipe-borne vibrations of up to 1 G, pressure surges, and temperature shocks have no effect whatsoever on the measurement. The distance between two consecutive vortices corresponds to a defined volume of fluid. Therefore, total flow can be calculated by counting the vortices that pass. The higher the flow velocity, the higher the measured frequency of vortices. In some applications, the velocity is too low for perceptible vortices to form. However, the velocity can be increased simply by installing a vortex meter that has a reduced cross-section. This modification does not affect the measuring accuracy. Functionality can be enhanced by incorporating optional temperature measurement into the sensor. A configuration like this, together with a built-in flow computer, can calculate temperature-dependent mass or energy flow. This feature is particularly important in industrial processes involving saturated steam or gases. In today's marketplace,
okay. Does it work with laminar flow? Okay, Basma, does it work with laminar flow? We've done this section already. It's your turn. Yes or no? What?
Yes, sir.
Do you, if you don't know, you get 0 for sure, but if you guess, you want to guess is laminar flow, does it work for laminar flow? By itself, without any modification, if we have laminar flow through the vortex flow meter, does it work? No, laminar flow doesn't form vortex, only if we have turbulent flow. We need turbulent flow to create those vortex. That is why if we have laminar flow, they try to increase the velocity by reduce the cross-section area, you see? There's some modification, reduce the cross-section area and we flow faster. It said in some application, did you watch the video? In some application, the velocity is not high enough to create a vortex. So they reduce the cross-section area, so the velocity is going up and it becomes turbulent and then it forms vortex. And then we count the number of vortex. Good? So vortex doesn't form in laminar flow. Okay? But if we sell gas, sometimes, but we always have pressure drop, right? But maybe just a little bit less. Coriolis flow meter will show the slow flow rate, right? Pressure drop related will show something. But this vortex thing, if we don't have turbulent flow, it doesn't work. And next one, ultrasonic.
Principle can be traced back to the English physicist and Nobel Prize winner Lord Rayleigh. His book on the theory of sound, published in 1877, describes the propagation of sound waves in solids and gases. Here is how this measurement method works. Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, the ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor. In this example, with a two-traverse installation, the clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example in the water and hydroelectric industries. Flexible mounting, process safety, and cost effectiveness are the distinctive advantages of ultrasonic flow measurement.
It just say Andres House at the end, okay, that's a brand. What is the working mechanism for this? Do you get it? The point is to know what is the working mechanism of each kind of flow meter, and you should know that, okay? The working mechanism of this is the measuring the flow rate based on the difference in the time required for the sonic wave to travel. Okay, the transit time for the wave go along the flow direction will be less, or wave travel faster. When it go in the opposite direction, it travel slower. Based on that difference, then we can know how much is the flow rate. Okay. And you a little bit more and we will be done, okay?
Positive displacement flow meters divide a flow stream into fixed known volumes and count them to determine the total flow and flow rate. In a gear meter, the measurement chamber is created by the gaps formed between precision-engineered gear teeth and the meter's body. As liquid pushes against the gear teeth, the gears progress and isolate a volume of fluid. As liquid continues to enter the meter, the trapped portion of fluid is carried along by the gears until the fluid is released into the downstream side of the meter. This process repeats itself continuously. You will notice the meter is impervious to intermittent or start-stop flows and changes in viscosity. This is unique to positive displacement meter.
So this is it's similar to gear pump, right? Is it? But for gear pump, we spin it for the fluid to move. But this one we use fluid movement to make it spin and register how many times it spin. Okay. So this is positive displacement type. The rotary vane type, rotary vane flow meter, that is on the lab unit. Okay. Electromagnetic flow. This one has some.
Who in 1831 discovered that electrical current can be generated with a magnetic
What's his
field.
name? We skip his name, but I think it's okay.
Roughly 100 years later, the Swiss inventor and priest Father Bonaventura Tirlimann applied this knowledge to electrically conductive liquids flowing in pipes and built the world's first electromagnetic flow meter. Let's take a closer look at how this measurement method works. Two field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. Two electrodes which can pick up electrical voltages are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known tube cross-section, the flow volume can then be calculated. The greater the flow velocity, and thus the separation of the charged particles, the greater the electrical voltage between the electrodes. The electrodes also detect what is called interference voltage, which has to be separated from the actual measuring signal. One method that has been successfully used for this purpose is to create the magnetic field with a pulsed direct current. To do so, the polarity of the magnetic field is alternately reversed, illustrated here in slow motion. The voltage picked up on the measuring electrodes now constantly changes in polarity.
Okay, we don't use this, right? But just so you know that we have some kind of this. We don't use this on the lab unit. But one point to know is, very frequent, people try to sell something about the magnetic thing, magnetic flow conditioner, electric flow conditioner. They must be able to tell you the working mechanism. If they cannot, don't buy it, okay? But this one is have a working mechanism and is tested and verified. And I think this is the last one. Daniel Senior Olympic. Oh, it's unavailable. It's not there anymore, okay? We can take it out. This is the operational sequence. how do we take the overfit plate out, okay? And to do that, it is like this, okay? Take the plate out, turn it, put this plate in, turn it, separate the pressure inside, replace the plate, put the new plate in, put the something on the top, and then we can separate it. So this is serial fitting. This fitting itself It's not a flow meter. Okay. It's just a fitting to hold the orifice plate. Okay. The actual measurement comes from the pressure drop. Okay. We convert the pressure drop to flow rate for the orifice plate. Hopefully you can accept the last one. Okay. Electromagnetic flow meter that uses an electric field that it separate the charge, generate the current, and based on how much current generated, we know how fast it flows. The rest, you should be able to tell the working mechanism. Okay, working mechanism of rotary flow meter, vortex meter, positive displacement, rotary meter, sliding vane. So, and the one that we use is a sliding vane. Okay. For each flow meter that we use, we need to know where's the error coming from. Okay, in what case that it can do the measurement, in what case that it cannot do the measurement. For example, the electric charge that you just see, they do the measurement with water, right? If you have oil, there's no electric charge. The molecule is non-polar. Does it work? It may or may not work, okay, or it may work differently. One of the considerations is that I want to emphasize is the maintenance requirement. Okay, anything that we put inside the pipe, we have to maintain it. Okay, especially if it's obstruct the flow, like orifice plate. Over the time, some solid particle may hit it. Okay, and it may make some defect. And we have to change it. If it has some defect, it doesn't do the measurement accurately. Same thing as a coriolis flow meter. But coriolis flow meter, there's no obstruction, right? You just change the flow direction and there's a vibration. So that's have less maintenance. Okay. Positive displacement type measure the volume directly, and the one that we use on the lag unit is A.O. Smith sliding vane. Okay, and this is the one that we use. Diaphragm type, we use it for residential gas meter. At home, we measure how much gas that we use. Okay, how much natural gas. It counts the volume directly too for sliding vane, and this is how the calculation was done. Like the number of reaches, the number of registration multiplied by each volume. Okay, we don't focus much on that. We will focus more on the orifice plate. Okay, and the only name for the next one is vena contracta. I keep talking about this, okay, but later I will ask you. The point where the velocity converge and this have facet velocity we call vena contracta. Just that. Thank you for coming. If you have university skills, do not come to Thursday field trip, but can go to Friday field trip. Come to see me. If you have university skills, do not come to Friday field trip, but can come on Thursday field trip. Come see me. Okay. I have 2 students for not coming on.